In this lesson, we'll talk about properties of trigonometric functions of real numbers and some trigonometric identities. Let's recall what a unit circle is. A unit circle is a circle with the center at the origin and the radius 1. So the unit circle has equation x squared plus y squared equals 1. We can look at the point moving on the unit circle. The position of this moving point at any given time defines an angle from the x-axis till the terminal where we can find the point. Since the length of the arc in a unit circle numerically is exactly the same as the central angle subtended by this arc in radians, therefore we can assign for each angle this length. Let's unfold this length. Imagine this is a thread and just try to straighten it out on the vertical axis as on the diagram. And then even further, let's rotate this point onto the x-axis. And a point obtained that way will be exactly at the distance theta from the center. So every angle can be actually placed on the x-axis by using this type of transformation. That also allows us for using angles in all real numbers. That means angles that are going farther than full rotation, for example, more than 2 pi or even negative ones. And remember that each such point determines the values of all 6 trig functions, because those values are defined in terms of x, y, and r. Well, in our case, r is equal 1 because that's a unit circle, so this distance is 1. So the definitions of our trigonometric functions, for example, sine of the angle theta, would be y over r, but since r is 1, it will be just y. Okay, great. But as we said, the angle theta could rotate many times around, so we actually can cover any real number. So, for example, the same y will be attached to the angle theta, and theta plus 2 pi, and theta plus 4 pi, and theta plus 6 pi, or theta minus 2 pi. And since this angle will be identified with any real number, instead of theta, we could use t to depict the fact that the input for sine can be actually any real number, any point on the x-axis. So instead of sine theta, we can say sine t is equal y. Similarly, cosine t will be equal x over r, but r is 1, so it's just x. Tangent t will be the ratio of y over x except for when x is 0. If x is 0, that means these 2 points will not produce any value for tangent. Tangent of those angles won't exist. And similarly, the reciprocal functions are defined as before, except that instead of r, now we have 1. So functions created this way, instead of looking at the angle, we're looking on the point moving on the number line, which corresponds to the angle. Such functions will be called circular functions. So the definition of circular functions is as follows. Those are trigonometric functions defined by coordinates of a point on a unit circle with domains of real numbers corresponding to radian measurements. As we already observed, the same point on a circle will actually be marked many times, infinitely many times on the x-axis. Anytime you go around the circle and hit the same point, and again, and for each trig function, that point corresponds to a specific value. So this value will repeat itself every 2 pi for sine and cosine. It's slightly different for tangent because, for example, this point will produce the same value as the point on the opposite side of the circle, because it's a ratio of y over x, and the coordinates of the opposite point will be negative x and negative y, so the ratio will still be the same, y over x, because the two negatives cancel each other. So in case of tangent, this situation will repeat itself every half a circle, that means every pi. And those will be periods of our functions. Obviously, the inverse function will carry the same properties. So the periods for cosecant and secant will be the same as sine and cosine, that means 2 pi. And the period of cotangent will be the same as period of tangent, which is just pi. Notice that a point on a unit circle that cuts off the arc of the length t, this t corresponds to the angle t, that's the same. Such a point will have coordinates cosine t and sine t. Well, why it is so? Cosine t, that's the x-coordinate. So if I project this point here, this distance will represent the value of cosine t, and sine t is equal to y. So that vertical distance represents sine t. So this is x, this is y. Therefore, the coordinates of the point P can be expressed in terms of cosine t, which is our x, and sine t, which is our y. Now, using properties of a unit circle, let's find domains and ranges of the 6 trigonometric functions from sine to cotangent. So we'll organize our information about domain and range of particular function in a table. If we talk about sine of t as a function of t, remember t is any real number, and this real number really corresponds to an angle in radians. So the domain of sine is all real numbers, not a problem. The same will be for cosine. The domain will be all real numbers, because we can use any angle and be able to detect what's the y, remember that corresponds to y, coordinate of a point, and what's the x, coordinate of the point. What about the range? Well, since we're talking about unit circle, then how high or how low coordinate y of a point on the circle can be? Well, this is -1, this is 1. So from -1 to 1, any value from -1 to 1 can be obtained. What about cosine? Well, cosine is the x coordinate of our point. So if we have a point, the x coordinate is this distance. Well, this point can go around the circle, and at any moment we have a corresponding x coordinate. So this x can go again from -1 up to 1. So range is -1 to 1 again. If we talk about tangent, as we remember definition, that was y over x. So tangent will not be defined when x is 0, and x happened to be 0 for these 2 points. So the corresponding angle to these 2 points is either pi half or 3 pi half. So pi half, and then add another pi, and then add another pi, and add another pi. So any multiple of pi you can add to the point pi half. Therefore, the points that we have to exclude from the domain are pi half, and then any multiple of pi. So we can record the domain as follows. It's all real numbers except for the points of the type pi half plus any multiple of pi, where this number n is an integer. So could be positive, could be negative. What about the range of tangent? Well, if we produce the ratio y over x, for example, if our point is very close to x-axis, then the y is very small and the x is nearly 1. So very small, nearly 0, yes, we can produce any number from 0 up to, and let's see what will happen when the point is close to y-axis. Well, then the y is nearly 1, but the x is nearly 0. So if I divide 1 by something very small, nearly 0, then I can obtain any large number that I wish. The overall fraction can be as high as we want to. Obviously, this situation happens for the negative numbers as well. Therefore, the overall range is all real numbers. Now, when we look at the reciprocal functions, cosecant is a reciprocal of sine. Therefore, the domain can be any real number except for those numbers t that will make sine 0. But when sine is 0, when y coordinate is 0. I will redraw the circle. Y coordinate is 0 for these 2 points. So these 2 points translate into angle 0 or pi. So any multiple of pi is not good because then the denominator will be 0. Therefore, we can state that the domain of cosecant is all real numbers except for those, t must be different than any multiple of pi, n pi, where n is any integer. Double braced set. Well, what about the range of cosecant? Since cosecant is really 1 over sine t, and sine has a range from -1 to 1, so if the sine is very close to 0, we create very high number, very large number. It can go up to infinity. But if the sine is approaching 1, then the reciprocal will be just 1. And we can't create something like 1/2 because then sine of t would have to be 2. So we can only obtain something from 1 to infinity for positive numbers. And the same situation happens for the negative numbers. Again, if I have a number very close to 0 but negative in the denominator, then the fraction is very high but negative, so from minus infinity. But the largest negative number that I can obtain is actually -1, and it happens when sine of t is -1, so up to -1. And that's a union. So that's the range for cosecant. Secant can be analyzed very similarly as 1 over cosine. So we need to get rid of points that will make x-coordinate 0. But x-coordinate 0 happens to be at these angles. That means at pi/2 and then plus any multiple of pi. So t must be different than pi/2 plus any multiple of pi, where n is an integer. And similarly as before, since we are taking reciprocal of cosine, the range will be the same as for reciprocal of sine, from -infinity to -1, union from 1 to infinity. Finally, cotangent. Cotangent is the same as x over y. So what we need to get rid of is the points that will make y coordinate 0. And as before, the points with y coordinate 0 are at the angle 0 or pi and any multiple of pi. Therefore, the domain of cotangent is all real numbers except for those that are of the type n pi, where n is any integer. So any multiple of pi has to be excluded. Now the range of cotangent, similarly as tangent, it will be all real numbers. We can actually produce any real number just by taking points that will have a lot larger x than y or nearly 0x. Okay, so we developed those properties of the 6 trigonometric functions as a matter of domain and range. The domain and range will be easier for you to remember when we start graphing those functions, so we can remember the graphs. And then it's easy to rate domain and range. But even without the graphs, just by looking at the ratios of x and y, we can still discover the properties. So maybe let's fill this up. That was 1 over y. And this one was 1 over x. We mentioned before that our circular functions are actually periodic. What does this mean formally? A function f is periodic if and only if there exists a positive number p such that the value of the function at t plus this p is equal to the value of the function at t. And that happens for all t's from the domain of the function. So, for example, that really means that if I have a value of a function for this particular t and it's somewhere here, and I will go p steps farther, so that's t plus p, then I will hit exactly the same value. And this repeats itself for every t. Therefore, if this is t that we start with, the next one will be somewhere here, t plus 2p. And we'll have still the same value, and t minus p, and will have still the same value. So that's the idea of a function being periodic. Now, if we choose smallest such p that our function will have this property, the smallest p is called the period of our function. Are the circular functions periodic? Well, we already noticed on the first slide that if we have a point P, which determines the value of our all trig functions for the input t, then this value will be exactly the same after the full rotation to pi. And that happens for sine and cosine. Therefore, the period for sine is 2 pi. And we can say that sine of any value t plus any multiple of 2 pi, which could be recorded as 2k pi where k is an integer, has the same value as the original sine of t. So that would mean that this 2k pi for any k really makes this sine periodic. And the smallest such number is when k is equal 1, so it's just 2 pi. So we're talking about smallest positive number that will create a period. That's why it's 2 pi. Similarly for cosine t, when we look at the x-coordinate, then this value will repeat itself after the full rotation to pi. So the period is 2 pi, and we can record that cosine of t plus any 2k pi will have the same value as the original cosine of t. Now, secant and cosecant are related to sine and cosine. Secant is reciprocal of cosine, therefore its period will be the same. So it's also 2 pi. And cosecant reciprocal of sine, so it's 2 pi. And similarly as before, we can claim the following identities. Secant of any number t plus 2k pi has the same value as the original secant of t. And the same with cosecant of any number t plus 2k pi gives us cosecant of t. Now, the tangent is slightly different because, as we remember, tangent is y over x. So a point with coordinates x, y gives you tangent y over x, but also a point with coordinates negative x, negative y gives you the same tangent. So tangent of t plus pi, which is here, also gives us y over x because the two negatives cancel. So tangent repeats its values after each pi. Therefore, the period of tangent is pi. And we have identity tangent of t plus k pi equals tangent of t. Similarly, cotangent, this is reciprocal of tangent, so it will have the same properties as a matter of period. So period is also pi, and we can write cotangent of t plus k pi equals cotangent of t. Let's analyze symmetries that we may have. For example, sine corresponds to y. So if I have a point with coordinates x, y, this is the y, and if I choose symmetrical point but with negative t, the y value will also be negative. Therefore, we can say that sine of negative t, which is sine of that angle, is nearly the same as sine of t, but with opposite sign. So it's the same as negative sine of t, because that's our y. So we have negative y. If we can take the minus outside of the function, this is really the definition of a function that is odd. So since sine is odd, its graph should have symmetry in the origin, because any odd function is symmetrical in the origin. Since cosecant is a reciprocal of sine, it will carry the same properties, so we still have negative cosecant of t, which makes it odd as well. Therefore, the symmetry of the graph is symmetry in the origin. Now let's look at cosine of negative t. Cosine of negative t gives us the same x because cosine is x coordinate. So it doesn't matter if it's cosine of positive t or negative t. The x coordinate of these 2 points is still the same. Therefore, cosine of negative t is the same as cosine of t. And similarly, secant is the same as secant of t. So these 2 functions are even. Therefore, we have symmetry in y-axis. They open like a book. So something like that, for example. And finally, tangent. Tangent of negative t, well, that's like negative y over x. And tangent of t will be y over x. Okay, so they change the sign. Therefore, tangent of negative t is negative tangent of t. So again, it's odd function. Therefore, we have symmetry in the origin if we look at the graph. And cotangent as reciprocal of tangent, we have the same property. We can pull the minus out. So again, it's odd, and the graph is symmetrical in the origin. Okay, we have a couple questions to practice on. Determine whether the function is even, odd, or neither. To check if something is even or odd, let's figure out what f of negative x is. Well, if I place negative by the x and square it in cosine negative x, then this is the same as x squared, and cosine negative x is the same as cosine x. So I end up with the original function f of x. Well, what does this mean? It means that f is even. So that's even. Let's do the same with g. Calculate g of negative x. It's negative x over secant negative x minus tangent of negative x. Okay, secant is a reciprocal of cosine, and cosine is even. Therefore, we can neglect this minus, and that's the same as negative x over secant of x. Tangent is odd, so I can pull the minus outside, and it will make it plus. So it's plus tangent of x. How this relates to the original function g of x? Well, it's enough to pull the minus outside of the bracket to see that the inside is exactly our g of x. So we really have negative g of x. That tells us that the function g is odd. Let's try the next one. H of negative x equals 1 plus cot of negative x, and cotangent is odd, so we can pull the minus out. So as you see, this is not the same as h of x. Is it the same as negative h of x by any chance? Well, no, because negative h of x would be negative 1, negative cotangent x. Again, that's not the same. Therefore, we don't have any symmetry here. It's neither odd nor even. Therefore, h is neither odd nor even. Now we want to find the exact value of the following expressions. Secant of a negative angle. First of all, secant of a negative, it's a reciprocal of cosine, which is even, so we can forget about this negative and we can write 1 over cosine of 7 pi 6. And then recall, to calculate something like this, we need the reference angle. So a reference angle for cosine of 7 pi 6. 7 pi 6 is more than pi by 1 pi 6. So the reference angle is really pi 6 here. And cosine in the third quadrant is negative. So this value will be negative cosine of pi 6. And now we use special triangle. half of equilateral triangle, 1, 2, root 3, to find out the exact value of this expression, 1 over negative cosine of pi 6, which is this angle, is root 3 over 2. So root 3 over 2, when we flip it, it becomes negative 2 over root 3. And after rationalization, that becomes negative 2 root 3 over 3, exact answer. And finally, cotangent of 13 pi thirds. Well, 13 thirds is like 4 and 1/3. But 4 pi we can get rid of at once because cotangent has a period of pi. So any multiple of pi can be actually forgotten. And we can rewrite this as cotangent of pi thirds. And again, referring to the special triangle 1, 2, root 3, pi thirds is this angle. So cotangent is 1 over root 3. And after rationalization, that will be root 3 over 3 as our final answer. Now the next question asks us to use a calculator to find approximate values of these expressions up to 4 decimal places. So that's something that you can do on your own, except that you need to remember to convert cotangent into 1 over tangent because you don't have the button cotangent. So 1 over tangent, and the negative we can already take out, and it will be pi fifth. So plug this expression to the calculator, and your answer should be approximately negative 1.3764. Similarly, cosecant, change it into 1 over sine of 251. Make sure that your mode is in radians, and then evaluate. That's approximately 1.6937 up to 4 places. The next question asks us to use the unit circle and the definitions of trigonometric functions to verify this identity, that sine of t plus pi is the same as negative sine of t. So what we really need to do is to analyze this diagram and justify this for ourselves, that sine of t plus pi, if this is t plus pi, that's the terminal of angle t plus pi. So sine defined by that point is y coordinate of this point. So it's really negative y. So we know that this is negative y, and sine of t, that's actually just y. But we have a minus in front. So yes, that's true, it's the same. If I negate the value of sine of t, which is this y, I obtain the value of sine of t plus pi, which is negative y. Next, we want to rewrite each expression in terms of the given function. So that's a preparation in proving identities by using properties of functions that we already know. So cosecant t over cotangent t, I want to change it in terms of secant. My suggestion would be to stay away from the last 3 functions. Try to change everything into sine and cosine, unless you see particular pattern that you can simplify quickly. But usually changing into sine and cosine works very well, and you can simplify expression to the desired form. So cosecant is 1 over sine. And then we divide by cotangent, which is cosine t over sine t, because the reciprocal of tangent. Okay, so just change this main division into multiplication of reciprocal, simplify complex fraction, and we see that some things will cancel. The sine cancels, and we end up with 1 over cosine. But 1 over cosine is the same as secant t, what we're supposed to show. In the next question, we want to rewrite cotangent in terms of cosine. If we know that the angle t is between 3 pi half and 2 pi, that means it's 4th quadrant. So if we recall cast, tangent and cotangent behave the same way in particular quadrants as a matter of signs. So in the fourth quadrant, the cotangent will be negative. So keep that in mind. And now cotangent is the same as cosine over sine. So that's already closer. We already have cosine, but we don't want to have the sine. So what we can do here is to use Pythagorean identity, the fact that sine square plus cosine square is 1. That's something that we use very often. And when we solve this for sine, at the last moment, because of the square, we need to make decision. Is it plus or minus square root of 1 minus cos square t? Since we just figured out that our cotangent must be negative, so when we solve this expression for sine t, we are using the negative option. So that's equal negative root of 1 minus cos square t, just because our angle is in the fourth quadrant. We can also look just at the sine. The sine must be negative in the fourth quadrant. So we change cotangent into expression that involves only cosines. And the last example, we want to change this expression in terms of cosecant. If I see two fractions, the first thing that comes to my mind is try to add them. In order to add them, I need common denominator. But the common denominator is the product of these two, which actually is the difference of squares. So it's like 1 minus cos square t. Okay, what's in the numerator? Well, if you multiply the denominator, we'll also multiply numerator. So 1 times this, 1 plus cos t, plus 1 times that. So 1 minus cos t. Okay, the cosine cancels. So we end up with 2 over, and 1 minus cosine square t, again from Pythagorean identity. You will see that we are going to use this very often, so get familiar with it, is equal to sine square t. So 1 minus cosine square is equal to sine square. Okay, but we need to leave the answer in terms of cosecant. However, 1 over sine is the same as cosecant. So we have the 2, and we have cosecant square t. Final answer. Perform the operations and simplify. Well, it's cosine minus a fraction. Why don't we put this under common division bar and see what will happen? Cosine t, that means I need to multiply this cosine, so it's cosine square t minus 1. And that reminds me of Pythagorean identity. It's not exactly the same, but who knows, maybe we can take something from it. So that's our Pythagorean identity. If I get cosine square minus 1, if I bring the 1 to the left, and I bring the sign to the right, so cosine square t minus 1 is negative sine square t. So using this, rewrite the numerator as negative sine square t over cos t. So we already subtracted and we simplified. We can also rewrite this in equivalent form by saying sine over cosine is the same as tangent. So I can say this is negative sine, separate one sine, and the other sine over cosine will be tangent t. So negative sine times tan t. In the second question, we need to multiply these two brackets, so we end up with secant square t, it's a difference of squares, minus 1. Again, recall the Pythagorean identity. 1 plus tangent square theta is equal to secant square theta. So that's another version of Pythagorean equation. We proved this in the previous lecture. So we can use secant square minus 1 is the same as tangent square. As you see, the Pythagorean identities are really important. We have to memorize them. And the last example, again, we have two fractions, we need common denominator, but I would prefer to have everything in terms of sine and cosine. So what we could do is multiply this fraction by cosine in the top and in the bottom. Why cosine? Oh, because tangent is sine over cosine and secant is 1 over cosine, so the cosine from denominator will be cancelled. So what I really have is 1 minus sine t over cos t, and then it's minus cos t over cos times tangent is just sine, and cos times secant, which is 1 over cos, is 1. Now we're ready to add them by using common denominator. We have cos t times 1 plus sine t, and in the top, the 1 plus sine t, you can change the order because addition is commutative, so we can multiply these two. That becomes difference of squares. It's 1 minus sine square t minus, and then we multiply across these two. Cosine times cosine is cosine square. Now watch that if we pull the minus outside of the bracket, we really have 1 minus, and that's sine square plus cosine square, which is another 1. So no matter what the denominator is, the whole expression will actually be 1 minus 1. This is equal to 1, so the whole expression is actually equal to big 0. Now, in preparation for solving equations, here's an exercise that asks us to factor each expression. In the first one, treat tangent t as a new variable. If you replace tangent t by x, this expression really takes the form of x squared plus 4x plus 4. So let's recall, how do we factor this? This is actually perfect square. It's a perfect square of x plus 2 square. Well, but x was our original tangent. So thinking that way, you can factor the expression into tan t plus 2 bracket square. Similarly over there, that's similar to the trinomial 2x squared plus 9x minus 5. So on the side, you may want to factor this trinomial, 2 brackets. It must be 2x and x. It must be 5 and 1, for example, like this. Let's try it. And the middle term must be 9. It's a difference between the inner product and the outer product. So inner product is 1x, outer is 10x. We want to have the overall plus 9, so we'll make plus 10x and minus 1x. That will make the factorization. So let's use this pattern, and instead of x, we're going to use sine. So this factors into 2 sine t minus 1 times sine t plus 5. In the following example, given that sine t is 1/2 and t is in the second quadrant, find the value of cotangent t. Well, what do we do? Let's model the first equation by drawing a right angle triangle. If this is angle t, that sine of it is opposite over hypotenuse. If this is 1, this is 2. Oh, that looks like a familiar pattern. Right angle 1, 2, and this must be root 3. But that works for t that is actually a reference t from the first quadrant. Our t is from the second quadrant. So we know that t reference from this triangle, it is pi 6. T reference is pi 6. Therefore, cotangent of t, not t reference but t, is the same as cotangent of the t reference as long as we accommodate for the sine. Since this is second quadrant and cotangent is negative in the second quadrant, then we have to use a negative sign here because of cast. Cotangent is negative in the second quadrant. Okay, so that's negative cotangent of pi 6. And then we can look back into the triangle. Cotangent of pi 6 is root 3 over 1. So overall we have negative root 3. Final answer.